Oke, selamat siang semuanya. Suara saya bisa terdengar? Halo, tes 1, 2, 3.
Terdengar, Pak.
Bisa, Pak.
Oke, baik. Oke, baik. Kita mulai saja untuk sesi ini. Jadi, sebentar. Oke, baik. Jadi sesi ini kita sudah masuk ke topik, ya, new topik. Topiknya adalah tentang basis of a vector space. Yeah. So this is one properties of the vector space. So this session we will learn all about the basis of vector space. Before I explain what is a basis of a vector space, we must know some terms and definitions, like okay, so this is the content of in this session, in session 5. Before we before we know what is a basis, we must know what is a linear combination and linear independence. And after that, I will introduce some basis of a vector space, and from basis of vector space we can define the dimension. And there is some special basis in vector space. If our vector space is also inner product space, then there are a special basis called orthogonal basis. So in this session and next session, session 5 and session 6, we will learn all about a basis of vector space. Okay, first definition, first terms about a basis. A basis can generate all vectors in a vector space. In linear algebra, generate translate to linear combinations. So suppose we have a set of vectors from V1 to Vn. This is a set of vectors. So we have n vectors in here. Suppose we have n vectors. And suppose that we also have n scalars from R1, R2 until Rn. So this is n scalars. Then from this n vectors n scalar, we can multiply scalar with vectors and we can sum. So we have the sum of scalar R1 multiplied to V1 plus R2 V2 plus until Rn Vn. This is a new factor. We can get a new factors from this operation. Then the new factor is we call this new factor is a linear combination of V1, V2, and until Vn. It means a linear combination is a factor that a factor we from this operation, scalar operation and sum of factors. And if we collect all linear combination of V1, V2 until Vn, then the set of all linear combination is denoted by span of V1, V2, and until Vn. So mathematically, this is the set of all linear combination. We can write R1 V1 plus R2 V2 plus blah 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 plus Rn Vn, where R1, R2 until Rn is scalars. Usually we take the scalars from real numbers. So span V1, V2 until Vn, span of this set is the set of all linear combinations. So the elements in the form of this one. And for illustrations, if we have only two factors, for example, let's say V1 is 1, 1, 1 in three-dimensional V1 these vectors, and V2 these vectors. One of the linear combination of V1, V2 is 1, 2, 3. So the factor 1, 2, 3 is a linear combination. Is linear combination of these two vectors V1 and V2. Why the factor 1, 2, 3 is a linear combination of V1 and V2? Because we can write 1, 2, 3 as a sum of scalar R1 times V1 plus scalar R2 times V2. If there is a scalar R1, R2, then we can conclude that 1, 2, 3 is a linear combination. What is the scalar? We can find the scalars by solving the linear system of linear equations. we can use Gaussian elimination or Gauss-Jordan elimination, and the scalar is 2 and minus 1/3. Is this scalar right? We can compute. So 2 times 111 plus 1 minus 1/3. If we can compute the right hand side, we get 2 minus 1. Second is 2 minus 0 and 2 minus plus 1. So we get 1, 2, 3. Because there is a scalar, there is a solution from these equations. Then 1, 2, 3, this vector is a linear combination. Okay. And what's other linear combination of 1, 1, 1, 3, 0, minus 3? For easy example, we just sum these two vectors. So, for example, 4, 1 plus 3, 4, 1 plus 0, 1, 1 minus 3 is minus 2. And these vectors also a linear combination of V1 and V2. Why this? This is also a linear combination of V1, V2 because this vector 4, 1, minus 2 is scalar times 1 multiplied times multiply 1, 1, 1 plus scalar R2 multiply 0 is 3, 0 minus 3. And what is the scalar? Scalars is 1 and 1. So 4, 1 minus 2 also a linear combination of V1 and V2. And we can we can, because the definition is for general vector space. So the example may be a vector in R4. For example, if we have 1, 1, 0, 1, and 2 is 2, 0, 3, 1, and what is a vector, a linear combination of these two vectors? Yeah, just you put two scalars. For example, 1 and this 2, we multiply the scalars with these two vectors. 1 multiply V1, 2 multiply V2, and we sum these vectors and we get a linear combination of these two vectors. So this is an example of what is linear combination. So a linear combination is a vector obtained from sum of vectors by scalar multiplication and sum of scalar multiplications. Okay, any questions for linear combination? Ada pertanyaan nggak mengenai linear combination? No questions? I think this definition already given in linear algebra. this definition, the linear combinations. Any questions about linear combination? So the first point is one of the linear combinations, and the second point is about what is a span of these two vectors. What is a span of V1 and V2? By definition, this is the set of all linear combination of V1 and V2. So this is the set of scalar R multiplies V1 plus another scalar S multiplied by second vector V2, and where R and S is a scalar from some field. We denote by F. We can choose this. We can replace F by real numbers or rational numbers or any field. So this is span of V1, V2. Span V1, V2 is the set of all linear combination of V1 and V2. And we, from the point 1, we can state that 1, 2, 3 is an element of span V1, and V2. This is just one element, an element of span V1, V2, because spans means the set of all linear combination, and 1, 2, 3 is one of the linear combination of V1, V2. Another element we can just put the number, the scalar R and the scalar S.
Pak,
So,
mau tanya,
yes.
itu yang RS elemen F itu maksudnya gimana ya? F-nya itu apa?
R and S scalar like numbers, like 2, S like 3. Jadi ini scalarnya tergantung dia ngambil di mana. Jadi it depend on what the field, what is scalar from. Jadi ini hanya memperkenalkan, introduce what is R and S. So, R and S is sembarang, arbitrary. Jadi karena ini set, kita nggak bisa nulis just R is 1, 1 plus 2, 3, 0 minus 3. Okay, we cannot write like this because this is the set all. So termasuk 1, 2, 3, termasuk tadi apa ya? 4, 1, 2, ya, termasuk. Jadi span is a set. Span is set. Span is a set. Sorry. Jadi kalau kita tulis span itu berarti kita bayanginnya kita itu dia adalah himpunan yang ada elemennya. Span is a set. And what is the element? The element is linear combinations. Paham nggak kira-kira?
F-nya itu pasti filled gitu, Pak.
F field. Field itu is a set but not only set, dia nggak cuma sebuah himpunan, but field must have two operation. So field is a set together with two operation. And usually these two operations is denoted by we call the operation on field is addition and multiplications. Addition, multiplications. For example, real numbers is a set. Real numbers, set of numbers, set of real numbers. But real numbers also have addition and multiplication. So real numbers is a field. What is other example of field? Complex number is a field because complex number has addition and multiplication. So complex number also a field. Another example is modulo like Z3, 0, 1, 2. This is also field, and the operation addition modulo 3, congruence modulo 3, and multiplications. Jadi F itu bisa kita ambil real, bisa kita ambil kompleks, bisa kita ambil Z-ris. Pokoknya semua yang sejenis dengan fields. Ya. Kalau mau tahu field itu apa, bisa back to previous session. Di situ ada definition of field. Kira-kira paham? Tadi siapa yang nanya?
Jelas, Pak.
Okay, any questions about linear combinations? So linear combination is a vectors from scalar multiplication and the sum, and the span of some vectors. Span is a set. What is the element? The element is linear combination. So span is a set of all linear combinations. Okay, now we move to the next definitions. So to define what is a basis, we must know what is a linear independence. So the first one is we must know what is a linear combination, and second is we must know what a linear independence. Because if we jump to what the jump to the definition of basis. Sorry if we no. Okay, so this is the definition of basis. Yeah. The definition of basis is the set of factors, a set of factors. This set we call a basis of for P, a basis for P if this set satisfy two conditions, all these two conditions. The first condition of basis, this set of factors must linearly independent. So you must know what is linearly independent. And the second condition for a basis is the span. This is the span. We already know what is span. The span, this is a set, all of the set of all linear combination. This set must equal to V, must equal the set of all element V. So we must prove if this basis, then this set must satisfy these two conditions. And we already know what is the second one. So now we move to the definition of linearly independent. So these two conditions all about the condition of a set of factors, a collection of factors. Okay. So a collection of factors V1, V2 until Vn is said linearly independent, is said to be linearly independent or is said linearly independent if these equations, what equation, the left hand side is the linear combination of, you can see that the left hand side, is linear combination, right? Linear combinations of V1 until Vn, but these linear combinations equal to 0. Be careful, this is not zero numbers, but this is a zero factors. Zero factors in V, zero factors in a vector space if V1 and Vn is a vectors in V. So the linear combination is equal to zero factors. The linear combination equal to zero factors if and only if the scalars are all zero. So R1 equal R2 equal R3 until equal Rn is all zero. This is zero in field. This is zero in field, and in linear combination itu zero of vector. Jadi nol yang pertama itu adalah nolnya. This is nolnya V, nolnya vektor. Kalau nol yang kedua, ya, the second zero is zero in field, zero of F, zero of real, for example, zero of complex, but zero in linear combinations is zero of V. Like if R2 vector 0, 0. And Otherwise, if the scalar is not zero, there is a non-zero scalars in some Ri, or then we say these factors linearly dependent. So you can see that the negation of linearly independent is there is some non-zero scalars that satisfy these equations. So in linear algebra terms, we can say that linearly independence, it means the solution of these equations is unique. So the solutions only get one possibility, all zero. If there is non-zero solution, then we say that V1 until Vn are linearly independent. Jadi linearly independent itu tinggal lihat si scalarsnya ya, scalarsnya apakah solutionsnya zero semua atau ada yang non-zero. Ya. So linearly independent we can say that linearly independence is the scalars, the only solutions is zero. The only solution is zero. The only solutions of scalars are zero, is zero, all zero. And the negation is if there are another solution, another non-zero scalars, if there are non-zero scalars that satisfy this equation, then V1 until Vn are linearly dependent. Look the difference. This is independent and this is dependent. Independent means the only solution of scalars is all zero. The negation is there are non-zero solution for the scalars. Okay. For example, if we have two vectors, say this is V1 and this is V2, and we want to know is these two vectors are linearly these two vectors linearly independent, then we must write the linear combination of V1 and V2. So we write R1 V1 plus R2 V2, and this linear combination equal to 0, 0, 0, 0 in vector space, 0 in R2. So the 0 in R2 is 0, 0. So if we want to know these two factors linearly independent, we must construct these equations. And then we must find the solution of R1 and R2. What is the solution of R1 and R2? sorry, this is 1 0 plus 0 1, and R1 R2 equal to 0 0. Jadi kita buat equation ini, ya. And then we find the solutions. What is the solution for R1 and R2?
0.
Yes, the solutions, and this is the only solution. This is the only solution. The only solution is R1 and R2 equal to 0. So we say that 1 0 and 0 1 are linearly independent because the solution is all 0. There is not no other solutions. Jadi tidak ada solusi selain ini. Look the definition. If and only if the solution is all 0, then we say that this linearly independent. These vectors linearly independent. And the second point is, are the vectors linearly, are these three vectors linearly independent? So we write this is P1, P2, and P3. Okay, we have three vectors, and using some argument, we write the linear combination first. We write the linear combination. Kita tulis linear combination-nya, and this linear combination we equal to 0 0. We construct this equation, and then we find the solution. What is the solution? Or is there another solution beside 0 R1 0? So the trivial solution is R1 equal to R2 equal R3 equal 0. This is the solutions, but the problem is there another solutions? Is there a non-zero solutions? Can you find non-zero solution for this equation?
-1, -1, 1.
Okay, -1, -1, R3?
1.
1. Okay, -1, -1, 1. Okay. So if R1 -1, R2 -1, and R3 3, is this also solutions? Yes, this is also the solutions. So we have R1 -1, R2 -1, and R3 is 1. This is also solution. So we get two solutions. We get two solutions, or equivalently, this is not the only solution. And we can conclude these three vectors are linearly dependent. Okay, linear independent because there are non-zero solution for the scalars. Okay, This is linear independent, and the second points are dependent. See the difference: independent, dependent. Okay, any questions? Linear independent? Ada pertanyaan nggak? Linear independent. How about if I only have one vectors? Say that 1, 1, 1, 1 is one is this vector are linearly independent or these vectors are linearly dependent. How about if we have one vectors? Is this linearly independent or linearly dependent?
Independen ya Pak.
Sorry, kenapa?
Independen.
Independent, independent. In or D?
In.
In. Okay, yeah, good. Right. If we have one factor, one non-zero factors, if we have a non-zero factors, if we only have one vectors, then this one vectors always linearly independent. Yeah. One vectors always one non-zero vectors always linearly independent. Why? Because we write the linear combinations R1, P1, and equating to 0, 0, 0. And the only solution R1 is 0. So it's satisfied the definition. Ya, jadi kalau cuma satu itu linear independent. Okay, any questions for linearly independence? So to check the factors, the set of factors linearly independent, first you must write linear combinations equal to 0 factors. This is the 0 factors. And then you find the solutions. Find the solutions. Solution for the scalars. Find the solution for the scalars. If you get only one solutions, if you get only all 0, R1 0, the solution is unique, then this linearly independent. This is linearly independent. But
Pak,
ya,
itu contoh kedua tuh dependent ya Pak?
Yang ini. Iya, ini linearly dependent.
Kenapa dependent ya? Bukannya kalau skalarnya 0 semua jadi 0.
Iya, tapi dependent itu problemnya adalah ada nggak solusi selain 0 semua? Paham nggak? Jadi kalau second example itu kan solutionnya ini solution nggak? Is this solutions?
Iya.
Iya. Okay. But problemnya bukan itu, problemnya Ada gak solusi lain? Ada gak solusi non-zero? Jawabannya ada. There is another solutions with non-zero scalars. We can find minus one, and 1. This is also solutions.
Jadi harus unik ya, Pak?
Yes, yeah. The solution must unique.
Only
The
the
solution
scalar
only
R
one.
must be 0 ya?
Yeah.
Must not be any other.
The
Okay.
solution must unique and the solution must be all 0.
Oke, Pak.
Second example, the solution is not unique because there is non-zero solution. Non-zero solution. This is non-zero solution. The solution must unique and the solution ya 0 semua ya. Coba. Okay. Okay, how about this? 1, 1 and minus 2, minus 2. Is this linearly independent? This is minus 2, minus 2. This is 1, 1. Independent or dependent? One minus
Dependent
2,
ya, Pak?
sorry?
Dependent.
Dependent, good. Yeah. This is linearly dependent because if we write the linear combination R1, 1, 1 plus R2, minus 2, minus 2, and equating to 0, 0, 0, and R1 0, R2 0 is solution, but the problem is there another non-zero solution? Yes, we have another non-zero solution. R1 is 2. R1 is 2 and R2 is 1. This is also solution. The solution is not unique. Okay, and we say that is linearly dependent. Ya. Yang jelas kelihatan sih kalau linearly dependent tuh biasanya kalau cuma 2 dia saling kelipatan. If there are only 2 factors, one must the kelipatan apa ya? Multiple of one factors. Now we move to the properties. The properties between this is the relation between linearly independent and linear combinations. Okay. So lemma 1, suppose we have m vectors. So we have m vectors, and these m vectors linearly independent. Okay. So assume that this linearly independent, and let W in V, this is a vector in V, W is a vector of V. And if we check these m plus 1 vectors, V1, Vm, and W, we check when these vectors linearly independent, then this linearly independent if and only if W is not linear combination of V1, V2 until Vm. Okay, you can see this is linearly independent, and if we add another factors, when this new set of this new collection, when this new collection are linearly independent, then where W must not a linear combination. Oke, jadi for example, if we have V1, V2, yeah, this is independent, linearly independent. And we add another factors, the third factors, say we have the third factors is W, and we ask, is this linearly independent? Is this linearly independent? Then we can ask, is W a linear combination or not? Is W a linear combination of V1, V2? If W is not a linear combination, then V1, V2, and W must linearly independent. And this condition is equivalent condition, if and only if. Okay. Because this is a lemma, so we can prove this statement. We must prove the if and only if conditions. How we prove the conditional statement? We must prove first. We must prove if these new vectors, if P1 until Pm and W linearly independent, then WW or W is not linear combination, is not a linear combination. And second, we must prove if W is not linear combination, if W is not a linear combination, then this new set are linearly independent. Okay, I will give the proof in 4. Okay, but I will prove only one direction. So we must prove if these vectors are linear independent, then W is not a linear combination. And the proof, the method of this, the method to prove this statement, we can use proof by contradictions. We can prove by contradictions. Okay, so we assume that this is linearly independent. Assume that linearly independent. So let's say this is the statement P, and this is the statement negation. Sorry, Q, statement Q. Let's say this statement Q. So if we want to prove this statement by contradiction, we assume that P is true and negation of Q is also true. So this is true and negation Q is true. So assume that V1, V2, Vm, and W are linearly dependent, and W, because this is not, so the negation of Q is W is a linear combination of V1 until V1. Okay, this is Q and this is negation Q. Okay. Because W is linear combinations, we can write W is equals R1 V1 plus R2 V2 plus dot Vn, sorry, Rn Vn. Okay. Since W is a linear combination, we can write W equal these vectors for some scalars, R1 until Rn. Okay, so W equals, and we move the left, all right hand side to the left. We move left. Sorry, we move all terms on the right to the left. So we get from this equation we get W, or we move W to the right, we get 0 equals to minus W. Okay. From the first equation, we move W to the right, and we get this. Okay. Or we can write this equal to 0. Equal to 0. This is and because minus W can we can replace this plus minus 1 plus minus 1 W equal to 0. Okay, now we have a linear combination of these vectors equal to 0. And from the assumption, these vectors are linearly independent. But if we look the scalars, we get, so we obtain R1, R2 until Rn Rn and minus 1. This is the solution of linear combination equal to 0. And there are non-zero scalars. So see, this is a non-zero scalars in these equations. And this fact contradict with our assumption that V1 and Vn until Vm and W are linearly independent. So this contradicts our assumption. Okay, because if V1 and Vm and W are linearly independent, then the solutions only 0, on all 0. Scalars are all 0. But in this equation, we get a non-zero. We get non-zero scalars. So this contradicts with our assumption. Linearly independent, only 0 solutions. And we conclude that this is must true. If these are linear independent, then W is not a linear combination. That's the proof of the first directions. And I will leave for the second condition, the proof of the second direction. Okay, and in lemma 2, we see that this is the implication of linear independence. So if suppose that these are linearly independent, these n vectors are linearly independent, and any linear combination of these vectors, yeah, or we can state that W in span. Remember, span means W is a linear combination. Then the scalars must unique. So then there exists a unique sequence scalars. So the solutions must unique. Okay. And we can simply say that if the set linearly independent, then the solution, if W is equal to linear combinations, with W linear combinations, then the solutions unique. Solutions is unique. Solutions is unique. Okay. For example, if we have 1 0 and 0 1, this linearly independent, and we find we take a linear combination. For example, 1 2 1 2 is linear combination of these two factors, and we write the linear combination of V1 and V2, A1 1 0 plus A2 0 1. Okay, then this scalars is unique. So the solution is unique. A1 must 1 and A2 must 2. Okay, this is lemma 2 else. Okay, we also can prove this lemma, but we did the proof. We move to the next one. Okay, this is a theorem about suppose that M vectors are linearly independent and each W1, W2, and Wm is linear combinations. Okay, this linearly independent, and each of these vectors also a linear combination of a second set, and we can know the numbers of M and which is greater. So if the first one are linearly independent and each of W linear combination of another, then the number of M must less than the number of N. Okay, for exercises, you can check whether 1, 2, 3, 4 is linearly independent or linearly dependent. Ada pertanyaan? Any questions? Until this. Ada pertanyaan nggak? Any questions? No? So let's get to the basis. So in the beginning, I said that every vectors has a basis. Okay, this is the main properties of a vector space. Every vector space has a basis. For example, R2, the vectors in two-dimensional, all vectors xy, where xy in real is real numbers. R2, this is a vector space over real numbers. R2 always R2 has a basis. For example, R2 has 1, 0 and 0, 1. This is the basis of R2. Another basis 1, 0 and 1, 1. This is also a basis of R2. But 1, 0, 0, 1 and 1, 1, this is not a basis. Yeah. This is basis of R2. This is also basis of R2. This is not a basis. Not a basis. Okay. If 1, 0 or 1, 0 also not a basis. If only one vectors in R2, 1, 0 is not a basis. Same with 0, 1 with 0, 1. If only one vectors in R2, 0, 1 also not a basis. This is not a basis. It's not a basis. So we can simply see a basis is we can generate all vectors in a basis. We can generate all vectors using a basis. And the definition of basis is a set of vectors. So this is a collection of vectors. A collection of vectors in vector space V is called a basis for V if these two conditions this satisfies these two conditions. V1, V2 until Vn are linearly independent. Remember linearly independence? This must linearly independent. And then the second condition is the span V1, V2 until Vn is equal to V. So we must prove all vectors in V, in V, we can write V as a linear combination. So V equal to R1 V1 plus R2 V2 plus R1 V1. So this is the meaning of the second condition. All vectors in V, then V is a linear combination of V1, V2, and until Vn. Oke, jadi ini pengertian basis ya. Basis itu harus dicek dua-duanya. We must check all these two conditions. If only one condition true, then this collection is not a basis. Okay, by the definition, the set 1010, sorry, this is my typo, 10 and 01. Okay. The set of vectors 10 and 01 is a basis for R2. And how about R3? We can check that 100, 010, and 001 is also a basis, is a basis for R3. Okay. And this special basis, we can denote 10 as E1 and 01 is E2. In R3, we can write 100 by A1, E1, 010, E2, and 001 is E3. And we can generalize these notations. Denote EI 000, the vector in Fn. So these vectors has n coordinates. Denote EI 000, but one in the ith entry, with all 0 except for 1 in the ith entry. And then the set of E1, E2, and En is a basis for Fn, where F is a field. And this basis we call the standard basis of Fn. So 10 and 01 is a standard basis. This is a standard basis. We call standard basis for R2. Or remember IJK in R3. One zero 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 001. This is standard basis. IJK standard basis. Okay. Next is a vector space only have one basis? No, because a vector space can have many bases. So 10 and 01 is not only the basis, is not on the only basis for R2. This is a basis for R2. But we also have another basis for R2. For example, we also have 10 and 11. This is also a basis for R2. Okay, we can check the condition of a basis. This is also a basis for R2. So a vector space can have many bases. And this is the properties of all bases of a vector space. So suppose that V1, Vn, and W are both bases of vector space. So this collection, the first is basis and the second one is basis for a same vector space. So this is basis for V and this is basis for V. Then we can conclude that the number of vectors must equal in the second set and the first set and the second set. Then n must equal to n. Oke, jadi kalau kita punya dua basis, ya, basis yang sama, maka banyaknya vektor di yang pertama sama yang kedua itu harus pasti sama. Ya. For example, R2 10 and 01 is a basis. How many vectors in this basis? Two vectors. Yeah. And we also have another basis, for example, 11 and 10. This is also a basis for vectors. How many vectors in this basis? Two vectors. This is the lemma. This is one important properties of basis. The number of vectors in a basis always same. Okay, that is any two finite bases of vector space have the same numbers of elements. So if the first one is 3 and the second basis is also have 3 vectors. And another basis of P also have 3 vectors. Okay, and the next one is a spatial basis in an inner product. So in a usual base, in a vector space, we see that in R2 there are a spatial basis called standard basis. Rn have a spatial basis called standard basis. So this is one kind of a basis in Rn. But in inner product, an inner space, Okay. Suppose that this is an inner product on a vector space V. So V has an inner product. We say that a basis and assume that this is a basis of V. But this basis is called an orthogonal basis. So this is one kind of spatial basis called an orthogonal basis. If the UI, if U1, U2, U3, until UN are mutually orthogonal. The meaning is if UI the product of ui and uj is always 0 whenever I different with j. So if we, for example, if we have only three factors, if we have three factors in a basis u1, u3, this is a basis, is a basis, is a basis for P. When this, we call this an orthogonal basis if the inner product of U1, if U1, U2 is 0, U1 and U3 is 0, the product of U1, U3 0, and U2 and U3, the inner product of U2 and U3 is 0. So if all this is 0, then this is orthogonal basis. Orthogonal basis. In addition, if we have an orthogonal basis and each norm of ui is equal to 1, or each ui is a unit vectors, the norm of ui is 1, we say that the basis is orthonormal. Okay, orthogonal means the inner product between two is 0. And orthonormal, not only the inner product equal to 0, but the norm of ui is equal to 1 for all in this basis. The norm must 1. Ya, jadi ortogonal itu harus saling ortogonal antara dua. Sedangkan ortonormal dia selain ortogonal harus normnya 1, atau kalau pakai inner product biasa dia panjangnya 1. Nah, what is the example of an orthogonal basis? For example, okay, sorry. The standard basis, 1, 0 and 0, 1. 1, 0 and 0, 1. Standard basis in R2. In R2, we have an inner product, the dot product. Remember dot product of R2. So R2 has an inner product. And if we check this basis, the inner product, the dot product of these two factors, and the dot product of these two factors is 0. So standard basis in R2 also orthogonal basis. So standard basis in R2 also orthogonal. But standard basis also orthonormal because the norm is 1. The norm of 1, 0 is 1, and now the norm of 0, 1 is 1. So standard basis in Rn using the dot product, together with dot product, because Rn has a dot product, then standard basis also orthogonal basis. So this is orthogonal basis, and standard basis also orthonormal basis. And the main result in an inner product space. Okay, this is the main result. So any finite dimensional inner product always has orthogonal basis. So next we will see how we find the orthogonal basis. From normal basis, we can construct an orthogonal basis. So this theorem tells we can produce an orthogonal basis from a basis, or from any basis. Okay. I think I will close this session because we have reached in. Okay, any question for a basis, orthogonal basis or orthonormal basis? Next, I will explain about how we construct an orthogonal basis. So the process to construct an orthogonal basis, it's popular. The process to construct an orthogonal basis is called a Gram-Schmidt theorem or Gram-Schmidt's process. So this is tells about how we construct an orthogonal basis, an orthogonal set. Okay, I think that's all for this session. Any question? Ada pertanyaan nggak? Kalau tidak ada, okay, I will close this session. Thank you for your attendance and your participation. See you next time.
Terima kasih, Pak.
Terima kasih.
Terima kasih, Pak.
Terima kasih, Pak.